Okay, here's a handy example about the invertible matrix theorem. I've got a simple little 2 by 2 matrix A here, and I've also got this transformation T from R2 to R2 given by T of x equals AX. So the invertible matrix theorem, abbreviated IMT here, tells us lots of things about square matrices. So 2 by 2 is square, n by n matrix in general is square. And the invertible matrix theorem is an if and only if theorem. It's a logical equivalence theorem. So all the statements in that theorem are either all true or all false. And one of the things that it says is that if I row reduce A, and in this case, if it row reduces to the 2 by 2 identity, then a lot of things are true, or I can say a lot of things about A. So one of the things that we can say is that the rank of A is 2. Now, in general, the rank is going to be n, where n is the size of the matrix. So here, A is 2 by 2. So n equals 2. So if you have a different size matrix, if A here were 3 by 3 or 7 by 7 or whatever, then n would be 3 or 7, etc. And so the rank would be equal to n if A is row equivalent to the identity. Another thing that we can say about A is that the column space of A is equal to Rn. Well, in this case, n is 2, so it's R2, and that is also equal to the range of T. Since T is defined by T of x equals AX, then the range of T is the same as the column space of A. Another thing that we can say is that the null space of A is equal to the set containing the zero vector, and that's also equal to the kernel of T. And then the last thing that we can say here, or that I'm going to say, there's a lot of other things that the invertible matrix theorem says. The last thing we'll look at here is that the dimension of the null space of A equals 0. Now these things are all true because A is row equivalent to the identity, which means A is invertible. If A is not row equivalent to the identity, then these things are all false. So it's false that the rank of A equals 2. Now that doesn't tell us what the rank is, but we know it's not 2. It's false that the column space of A is R2. So we don't know what it is. It's some subspace of R2, but we don't know what subspace. We'd have to figure that out, etc. But if A is row equivalent to the identity, then all these things are true just by the invertible matrix theorem. So if you have some exam or assignment that asks you to find these things about some given matrix A, all you have to do is row reduce it. If A is a square matrix, row reduce it, see whether it's equivalent to the identity or not. If it is, then you know all of these things.